Morning. All right, so let's start with number 1. Let me know if you have any questions. Feel free to jump in at any point if you have questions. All right, so helium is pumped into a spherical balloon at a constant rate of 25 cubic feet per minute. At what rate is the surface area of the balloon increasing at the moment when the radius is 8 feet? So the volume and surface area will be provided. Okay. So volume of a sphere, 4/3 pi r cubed. Surface area, sphere, 4 pi r squared. Okay, we know that, we just know we're going to have to involve derivatives here, so we'll just kind of get that out of the way. Okay, so derivative, v becomes dv dt. 4/3 pi is just the coefficient, that just stays. And then r cubed, we go through power rule there. Mm-hmm.
I don't know for this problem to take the derivative from the beginning, where some other problems you take it like more towards the middle.
I guess I'm just expecting it to be involved with my derivative process. I'm just expecting it, but yeah, I could have waited in the middle as well. I just want to get all the calculus out of the way, so we can just get that, but it's really up to you. Okay, 3r squared dr dt. Can do a little bit of cleanup here. I can take out the 3's in the numerator and denominator. S equals 4 pi r squared. I know how to involve that derivative. 4 pi stays, bring down to 2. Okay. So that's all the calculus in the problem. The rest, we're just trying to gather information and plug them into the appropriate equations. Any questions with derivative here? That's okay. Okay, let's read the problem here. Helium is pumped into a balloon at a constant rate of 25 cubic feet per minute. What variable can we assign that value to be? dv dt, right? Positive or negative? Positive, right? Getting pumped into a balloon. If you're having trouble deciding which variable a value goes with, look at the unit of measure, right? Cubic feet, that should tell us that must be volume. Minute must be time, so the only choice that we have is dv over dt, right? So we shouldn't really have to ever guess what value goes with which variable, right? We should have enough context clues to to be confident with the value that we're putting in place. Okay. Okay, so I'll put that down here. We know dV/dt is a positive. At what rate is the surface area of the balloon increasing? Okay, what are we looking for here? ds, right? ds dt. Surface area, we know that's s, but we see the word rate, we see the word increasing. Those two words describing surface area, we know it can't be a static value, it must be a ds dt. Okay, that's the unknown. When its radius is 8 feet, so that's a moment in time. All right, so really, we're just trying to piece this puzzle together. We have everything in front of us. We just have to see where things go. Okay, so ultimately our goal, let's start at the end. We know at the end we're trying to get the ds dt. And we do have a formula for ds dt. So if I want to solve for ds dt, all I need is r, and I need dr dt. Well, the good news is I have r already, so I can insert that in, but looks like dr dt is not quite ready for me to, I really don't have that information explicitly yet, but I do have dv dt, so maybe this dv dt equation can help us out in the meantime. Okay. So looks like dv dt is going to be able to provide me a link from dv dt to dr dt. So if I can find dr dt first, and that will naturally allow me to enter in and find that last missing piece to find my answer. Okay. So I'll go to my dv dt equation. Okay. dv dt is 25, r is 8, and our intermediate goal is to solve for dr dt so that we can insert that into ds dt. Okay. Do a little bit of cleanup here. 64 times 4 is 256. Use your calculator if you like. Solve for dr dt. So we want to divide the 256 pi over. Careful. 256 pi. That means the denominator is going to have this pi. Make sure that we don't just arbitrarily move that pi to the denominator, to the numerator if it's supposed to be in the denominator. Okay, I think we have everything that we need, right? We have r, we have dr dt. Both can be inserted to find ds dt. Okay. The pi's cancel out. Use your calculator. 64 times 25 divided by 256. This can reduce all the way to 25 over 4. Okay, and what's our unit of measure here?
Square.
Good, yeah, so, well, the square is gonna be with the surface area, right? So square feet is for the numerator, and then minute is for the denominator. So square feet per minute. Yes. Oh, why did I find the derivative of?
No, not why did
Oh.
you find
Oh, I did, right? I used dVdt. I plugged 25 into this equation. I just moved it over here.
Wait, then what is the 8?
Oh, right here.
Yes.
Yeah, 8 pi r dr dt, that's the derivative of my surface area equation. So I did derivative twice, once for volume and once for surface area, because I needed both. Okay, I'm going to skip number 2. Number 2 is more of the same. If you want additional practice, it's just a easier version of number 1 because you're only dealing with dV/dt. So I'll skip that. Let's look at number 3. Right, 2 cars start moving from the same point. One travels south, 60 miles per hour. The other travels west at 25 miles per hour. At what rate is the distance between the 2 cars increasing? 2 hours later. So you have 1 car traveling south, 1 car traveling west. We have a right triangle there, so we know we're dealing with a Pythagorean theorem problem. I'll go ahead and label them X, Y, and Z. You can do whatever you like. Okay, so I already know this is going to be a Pythagorean theorem problem. So I'm going to go ahead and set that equation up, get the derivative, get my calculus out of the way, and then just figure out what I need to plug in. Okay, x squared plus y squared, z squared. Okay, 6 variables to account for. Okay, so the key word here that we have to be careful about is 2 hours later, because this is going to really provide us information about the distance away from the starting point for these 2 cars. That's going to help us figure out X, Y, and Z. So 1 car travels south at 60 miles per hour. What variable can I put that in for? Okay, u over dt, positive or negative?
Positive.
Okay, positive because going away, increasing. Right, good. So don't pay attention to the direction. The direction has no bearing on whether we want our race to be positive or negative. imagine what's happening to that length. If you can imagine that length increasing over time, you want that rate to be positive. What that means is y is increasing at a rate of 60 miles per hour. The other travels at 25 miles per hour. I had mine being x, but you can have it depending on how you define your variable. Positive or negative? Positive still, because as the car moves away, we expect that distance to be, that x value for our triangle to be increasing. Okay, so we also have to be able to assign x, y, and z as well. Any idea what the length of x would be?
50.
Okay, why 50?
Because so it's going 25 miles an hour and the outsider says 25 times 2.
Right, so sometimes your distance is not given to you. You have to kind of figure it out on your own. So if we're moving at 25 miles per hour for 2 hours, he'll have accomplished, or he would have traveled 50 miles in that time interval. Okay, is everybody okay with that? Okay, same idea here, right? If dy dt is 60 miles per hour, he travels 60 miles per hour for 2 hours, 120. Okay, at what rate is the distance between the cars increasing? We're looking for dz dt. So the only thing that that's left to find before we jump into our derivative equation is to solve for z. And to solve for z, we can just use what? Pythagorean theorem, right? X squared plus y squared equals z squared. 50 squared plus 120 squared equals z squared. Solve for z. Use your calculator. And now the rest, we can just use our equation, right? Everything that we need is in front of us. All right, thank you. dz dt 65 miles per hour. Okay, so that's part A. Okay, any questions here? Okay, so yes, so now part B says find the rate of change of area of this triangle at this moment in time. So if we think about area here, area is 1/2 base times height. We can create our area equation first. We can worry about finding the derivative. So area 1/2 base times height. I'm using the variables that I've already created here. If I want to find dA dt, what do I have to involve here on the right side? Product rule, yeah. X and Y multiply together. Okay. 1/2 x's derivative is just 1/2 dx dt. Don't forget that time is independent variable. It's just not just 1/2. We have to keep track of that dx dt there. G prime, y's derivative is dy dt. Okay. Any questions here from a to dA dt? Because once you're here, it's easy. Then you just plug everything in from what you have from part A. No issues here? Okay. $1,500 plus $1,500. Area, all squared. Time interval is per hour. Okay, any questions so far? Yes.
Can you go over how you found?
Sure. So we have two cars starting at the same point. We know that the car moving to the west is traveling at 25 miles per hour. And it's asking what the dimensions are 2 hours later. So if you're moving at 25 miles per hour for 2 hours, you're going to cover 25 miles the first hour, 25 miles the second hour. So you're going to end up at 2 hours, 50 miles away from the starting point. And then same thing with 60 miles per hour here. 60 after 1 hour, 60 out with another hour there, 60 plus 60, 20. Okay. Good. Any other questions? Okay, turn the page. The shadow problem here. It's always going to be set up the same way. We have a triangle within a triangle. Call this X, I'll call this Y. The only thing that's going to be different is we have to assign those vertical parts there. A street light is mounted on the 15-foot pole. My street lamp there. A man 6 feet tall walks away from the pole with a speed of 5 feet per second. So as he's walking away, he's causing this X to increase. So we want that rate to be 5 feet per second. Okay, but let's do this. I just want to just get the proportion out of the way, and then we can, but you can do whichever order you like. I just want to just get this out of the way. So I know that this is going to be a similar triangle problem. The two triangles I'm dealing with, I have the triangle here. triangle here. So if I set a proportion here, I can say height of the small triangle is to the height of the large triangle as the base of the small triangle in red is to the base of the large triangle. So that is the equation that we'll be using. Any questions with the setup? Okay. If I cross multiply, I can at least get the denominators out of the way. I can combine like terms, get it ready, get my calculus out of the way, and then we can look to see where the pieces fit. Okay, so cross product here. Combine like terms. Derivative, easy equation, but just be careful that you produce your time derivatives there. So 6x becomes 6 dx dt, and 9y becomes 9 dy dt. Okay, let's gather some information here. The man walks away at a rate of 5 feet per second. So as he's walking away, we expect that x to increase, so we want that dx dt to be positive. How fast is the tip of the shadow moving when he is 40 feet from the pole? So tip of the shadow, there's a formula to this. It's dx dt plus dy dt. But before we can find the sum, we first have to find dy dt. And dy dt represents the rate of change of the length of the shadow. So the tip of the shadow is going to get influenced by how fast the y is increasing and also how fast the person is walking. So the two x's and y's increasing is going to influence how fast that tip of the shadow is moving on the ground. All right, so first we need to find dy dt, which we can do right now because we have a simple equation. Only thing that's needed is dx dt, and we can find dy dt. Okay, divide both sides by 9 to solve for dy dt. So the tip of the shadow is just going to be adding the two rays together, dx dt plus dy dt. Okay, 15 over 3 plus 10 over 3 is 25 over 3. Okay, that's part A there. Any questions? Okay, part B. Find the rate of change of the area. Area, there's two triangles there, meant to say for the large triangle. So just like before, we're going to create our area equation. Okay, look at how this is defined here. How would you say, what's the area of this triangle here? How would you set this up? But can we just say it's 1/2 x times y? Is that the way that this one is set up? Okay, so what would represent the base? X plus y. We don't want to say x times y, right? Because that's not quite the full length. It's x plus y. Okay. Okay. What's the height? Okay. Looks a little messy here. Well, I can just do a little bit of cleanup, right? I can take the 15 and 1/2 together, distribute it through, and I should be able to get an easy equation without having to go through product rule, right? There's no need for product rule here. Okay, I'm just kind of moving some coefficients around, so just make it a little bit cleaner. If I distribute that through, I should have a nice and easy derivative process here. Okay, derivative, a becomes dAdt. What's 15/2 x? What's 15/2 x's derivative? Yep. 15/2 is just a number. 15/2 y, same idea. Okay, so we just give the derivative what it needs. It needs dx dt, it needs dy dt. We just insert those values in. Use your calculator. 62.5. And what's our unit of measure here? Feet squared per second. All right, we've seen the variation of number 5 already. Let's skip that. And let's go to number 6. 6 is a limit problem, which could potentially be L'Hopital's rule. Number 7 is linear approximation. Okay. What's the first thing we do, though, if we see a limit problem? Always. If it's approaching a real number, we always do what? Yeah, do our substitution, right? Don't do L'Hopital's rule unless you get the green light. And the green light is 0/0. There has to be, they have to tell you, we have to be kind of confirmed that there's a hole before we can do L'Hopital's rule, right? We don't want to just jump into the process, because it's possible we could evaluate the limit at 1 and get a real number. If we do, then we stop, right? There's no need for L'Hopital's rule if there's no issue. Okay, so 1 in for x. Okay, you guys get 0/0. Okay. So now 0/0, there's a hole. There's a need for us to do more work on it. L'Hopital's rule is now going to come into play. Okay, this is be a tough problem to factor. So really relying on L'Hopital's rule. And that's, I would say, moving forward, if you see a limit problem, after you confirm 0 over 0, I would say for a lot of students, L'Hopital's rule is going to be an easy first option to go after. Okay, so L'Hopital's rule, we're trying to create a simpler version or really a different version of this problem so that hopefully we can reevaluate the limit and get to our true answer here. So derivative of the numerator, power rule, we get 3x squared. Denominator, 12x squared minus 1. Okay. As soon as you apply L'Hopital's rule once, you have to reevaluate. We can't just blindly keep finding the derivative before reevaluating. Okay. The only time we can do a L'Hopital's rule a second time is if we get another set of 0 over 0. So let's reevaluate. 1 in for x. Get 3. 1 in for x in the denominator. I get 11. 3 over 11 is the real number. That's my answer. There's no need to do any more work on this problem. We have our real number. We have our limit. Okay, questions with 6. Number 7, use linear approximation. I won't present the problem like this. I'll present the problem more straightforward. I'll say your function is 1 over cube root of x. And then the x value is at 8. And then approximate f of 8.04. So I'll present the problem more like this. Okay, but your first goal is ignore the decimal and just try to get to the tangent line equation, right? Take the 8, put into the function, get the order pair, work with the function, get it ready for the derivative, find the derivative, get the slope formula, plug 8 into the derivative, get the slope, order pair, slope, point slope form. Once you get your tangent line equation all nicely set up, then your final step is to work in that 8.04, that decimal value. All right, let's do the order pair first. Cube root of 8 is 2. Order pair is 1/2. My y value is 1/2. So I have my order pair. Set that aside. Let's go ahead and get our derivative. To get our derivative, we first have to do a little bit of cleanup. So 2 things I got to do. I have to get the radical to become a rational exponent. I have to push that denominator to the numerator to get it ready for power rule. Okay. We find our derivative once we get it cleaned up for power rule. Subtract 1 from the exponent. So minus 3 over 3, that's really negative 4/3. Okay. Once you find your derivative, you can evaluate the derivative at the point. I'm just going to do a little bit of cleanup before I enter fill that x with 8. Okay, so I have my slope formula. I'm going to now get to my slope. Use your calculator if you like. Even without a calculator, this is not too bad here because I can make that 8, do the cube root of 8, do the 3 first. Cube root of 8 is 2. 2 to the 4th is 16. 16 times 3 is 48. All right, right, so we're going to use the order pair and the slope that we gathered to create our tangent line equation. Okay, any questions getting to this tangent line equation? I'll do a slight adjustment here. I'm just going to move that 1/2 over to the right side, get y by itself, and then our final step, I'll work in that 8.04. Okay, any questions with this? I really think that you already know how to do this, which is that now we have a specific name for this process, right? It's putting the decimal into the tangent line equation, but really all of your, pretty much 95% of your work is just trying to get to that tangent line equation. Okay, let's do a cone problem. Number 2 on the next page. Okay, water's pumped into a conical tank, 8 feet tall, diameter of 10 feet. The water is being pumped at a constant rate of 3/5 cubic feet per hour. At what rate is the depth of water in the tank changing when the tank is half full? All right, we know that we're always going to be dealing with proportion here, so I'm gonna just redraw this portion and identify some parts that I need. Okay. Sometimes they give you the diameter, sometimes they give you the radius. If they give you radius, you keep it. If they give you diameter, make sure you split that in half. I'm just going to get my proportion equation out of the way because I know I'm going to need it. So radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. Cross multiply. So right now I still don't know which way to go about solving, but I know I either have to replace R or H, and I'm going to use the information get from the problem to help me decide which one to go after. So, all right, water is being pumped into a conical tank. Water is being pumped at a constant rate of 3/5 cubic feet per hour. Okay. What is that going to go in for? Or which variable is that going to go in for? dV over dt, you see cubic feet, that's must be volume per hour, that's time component, dV dt. water being pumped in. So we know that water is increasing in the tank. We want that rate to be positive. Okay, at what rate is the depth of water in the tank changing? What are we looking for? Wait. We know depth of water is height, but it's asking for rate of change. So which variable is that talking about? dH over dt. Okay. When the tank is half full. Okay, so I think I should have phrased this a little bit differently because the cone half full may mean different things. So I really just meant that when the height is at its halfway point. So when h equals 4. Okay, careful. This is the part that throws a lot of students off. They want to use this in the beginning, but this is for the end, right? The height of the water is not going to be used in the beginning. So that's the biggest mistake that I see with this problem, is just working that value too soon, trying to work it into the equation. So you really have to just remind yourself, do not use until the end. Okay, number one mistake. Okay, however, this is helpful in telling us which direction to go in, right? You have dH dt, we're looking for dH dt, we have h, so we have to make a substitution, right? That means we would prefer to get the radius to be out of the way so that h's are the only variable involved, and h's will just naturally produce these things for us. So I'm going to solve for r here, so I can replace r in my volume equation. There's my volume equation. I'm going to take this, insert it into the r. Now my volume equation should just be purely in terms of h. All right, that's one big hurdle. That the first hurdle that we need to be able to get through, right? Getting our equation in terms of the same, the correct and the same variable on the right side. Okay, the second major hurdle is, I think many of us know that we have to involve the derivative, but we take the derivative too soon. That is another issue that I see. You really want to spend the time to clean this up. You want all the coefficients nicely clumped together. You want your variable together. We don't want h's kind of all over the place. We really want everything to be just one h term. We want coefficients in front. But to do that, we got to spend the time to clean this up. So distribute, get rid of the parentheses, push all these things together here. Okay, so 5 squared, h squared, 64, or 8 squared. Okay, still not ready. Okay, still not ready. We still want to do a little more cleanup here. Let's get all this to be one nice fraction. Let's get the h's together. This is where we need to be before we find the derivative. Okay. All right, everyone okay with that? If you can get to this point, I feel confident that you're able to get to the end with minimal mistakes, because I think the hard part is to get to this point. Okay. We still have to find the derivative, but the derivative should be nice and easy. Just easy power rule with the coefficient that just hangs out in front. Okay, so v becomes dv dt. Coefficient stays. It's the h cubed that we're really after, right? H cube's derivative is 3h squared, but we don't want to forget what comes after this. dH dt, right? You can choose to clean up if you like, or, I mean, once you have your dV dt show up, you're ready to start inserting values in if you like. Okay, so we can replace dV dt with 3/5. Replace h with, now we can use the 4. Okay, now you're ready to use that 4. We will not use it anytime before this point. 4 goes in for h. Do a little bit of cleanup here, and then try to get that dH dt by itself. So dV dt gets replaced with 3/5, h with 4. I do a little bit of cleanup, use my calculator. This gets me all the way down to 25 pi over 4. I want to divide both sides by 25 pi over 4. Dividing by a fraction is the same thing as multiplying by the reciprocal. So 3/5 times 4 over 25 pi. Careful, pi is in the denominator, so it's going to have to stay in the denominator until the end. 12 over 125. Height is feet. Time is hour. Units of measure, feet per hour. Water is pouring into the tank, so we expect the height to be growing as well, so we're getting a positive rate that's consistent with what we were expecting. Okay, questions? Okay, with the remaining time, let me quickly go over a cylinder problem. This is the last problem here. So cylinder, the thing you have to keep in mind with cylinder is that even though your volume equation looks very similar, your first goal is try to get that radius to be replaced instantly, right? There's no need to hold on to the radius like how we did with cones. With cones, you can imagine that radius to be changing. But here, it doesn't matter what the water level is. Your radius is going to stay constant the entire way through. So this problem doesn't quite give you the radius. It gives you the area of the circular base. So we have to do a little bit of adjustment. We know that circle of area of circle equation is pi r squared. We set that equal to each other. We solve for r, we get r equals 5. Once you get that r equals 5, you're just trying to get that volume equation as cleaned up as you can. Replace that radius with 5. There's no need to hold on to that r variable. So whenever you see a cylinder problem, you should be expecting an easier problem. There's no similar triangles. There's no need to hold on to our radius variable. So as soon as that radius variable goes away, you can see your equation is already a lot cleaner to work with. We can jump directly into the derivative. V becomes dV dt. 25 pi. The h becomes 25 pi th dt. If you read the problem, water flows into the tank. 8 cubic feet per minute. Plug in 8 for dV dt. And that's all you need. Once you have that 8 for dV dt, I can divide the 25 pi over and solve for dH dt. Okay, one more thing. Careful. Cylinder problems tend to give you more information than you need because the information for the height of the container and height for the water level is needed for cones, but not for cylinders. So just be careful that sometimes you have these extraneous information that you're not going to use, but sometimes students force it into the problem, and that's why a lot of students do similar triangles because they feel like they have to use these values that are not needed for this problem.
Did you set this one up?
I'm sorry?
They're going in opposite directions.
Right. So they're going opposite direction, but we're just going to pretend like as if one is staying constant and then the other one is picking up all the rates.
Okay.
But you won't see one as complicated as that.
Okay.
Okay.
Thank you.
What?
So how did, because they're both going.
Right. So we're rearranging this. We're pretending like it's if B is not moving at all, and that A is going to take on both the rates so they can force it into a right triangle. So the fact that they're both moving apart from each other at,
So they're both moving.
yeah, so
It's different.
yeah, so they're both moving apart. So it's basically one moving away from the other at at 60 kilometers per hour. So it's like as if I asked you, I just told you, hey, one is moving at 60 kilometers per hour, the other standing still.
Will this be?
No, I'll give you one that's more straightforward like that.
Also, for the degree, we need to know the degrees, right? Like
What do you mean?
where like it's like 2x squared and then like a fraction and then on the bottom is like x cubed. Then you have to compare the degrees.
Only if its limits approaching infinity. Yeah.
So we need to.
Yeah. But you don't do L'Hopital's rule for that. L'Hopital's rule is only for if you get 0 over 0 or plugging in a real number.
So I was doing this one yesterday, and I don't understand why this is negative.
The reason why is because this is jet A, right? Jet A is moving towards St. Louis. What's happening to this x value?
It's getting
Smaller. So this is dxdt is telling us that this distance is decreasing at a rate of 500 miles per hour. So if you see the word decreasing, you got to put negative there.
And this one is this one increasing?
This one's decreasing as well because this plane is moving towards St. Louis. So y is decreasing.
So they're getting closer together.
Yeah, and the y, this length of the triangle is getting smaller. So anytime you can imagine a length getting smaller, you want that rate to be negative.
Okay, and also I just didn't really understand this one. Was this kind of like the other one?
Yeah, tip the shadow, you just add dx/dt plus dy dt.
Okay.
Set up your proportions. dy
Why do you
dt.
add them? I don't understand.
Oh, it says the tip of the shadow. Tip of the shadow is over here.
Oh.
So it's basically how fast that tip is moving on the ground. So that tip is moving on the ground based off of how fast the person is walking and how fast y is changing. So we add the two rays together to figure out how fast it's moving.
Okay. And then, so I was just wondering how to use L'Hopital's rule if it goes to infinity.
Infinity, just use the old rules. Just compare degrees. Don't use L'Hopital's for infinity.
Okay, thank you.
For this one, I'm not sure if this is a typo, but
Guys, I need all your book bags up front eventually.
you were 240 here. I got 140 when I plugged it in. Because 35 times 4 would be this is from 12 p.m. to 4 p.m.
Okay, so this one's a little bit interesting here because A and B are both moving in opposite directions. I'm not able to force a triangle out of it, so I'm rewriting the problem. I'm pretending like B is constant and A is picking up the speed of the other ship. So I'm adding those together to get 60. So it's like as if I said, oh, A is just moving 6 kilometers per hour to create that vertical change.
35 times 4 plus 25 times 4.
Well, it's 35 plus 25, which is 60, and I'm just using 60 times 4.
And that gives you your Z. Gotcha. Thank you.
I was absent yesterday and I was like sick all weekend.
You always have to like simplify the regular.
Otherwise, you run into an issue
Of having to go through product rule and power rule, and product rule, you don't want to do that.
Okay, thank you.
Mr. Nate, I'm so sorry. I put out my calculator for charge last night, and I forgot to put it back in my backpack. Do you have like an extra or? I'm so sorry. This will be good. Thank you so much.
Oh, I'm here. Yeah, I know. I got it. I'm about to fix this missing name. I have to get my self-confidence up.